So good morning Year 12. So we're going to look at 3 more trigonometric functions, and these are called our reciprocal functions. So if you remember, reciprocal means 1 over, or whatever you'd multiply by to get to 1. Okay? So our learning objectives, so we're going to learn the names of the reciprocal functions and their equivalent and what they're equal to. We're going to look at how to sketch the graphs of reciprocal functions, and we're also going to sketch transformations of the reciprocal functions. So let's have a think about what they're called to start with. So there are 3 new ones. Okay, the first one is called the cosecant, which we abbreviate to cosec theta, and that's 1 divided by sine theta. Okay, so cosec is 1 over sine theta. Sec, which is secant, okay, is 1 over cos theta. And then we have the cotangent, cot, which is 1 over tan theta. So you need to know these, and you need to be able to go from one to the other. You just need to recognise really that it's cosec is 1 over sine, which is the opposite of what you think. You'd expect it to be 1 over cosine, it's not. And the same here, sec is 1 over cos. Cotangent and tangent are fairly obvious that they're going to match together. Okay, you have to be really careful. These are different to the inverse functions that we looked at before, which were arc sine, arc cos, arc tan. Okay, the confusion often comes because we use sine to the -1 to mean inverse, but also -1 is used as the notation for reciprocal. But when we're working with trig, okay, we don't use the -1 as our reciprocal notation. Okay, we write it as 1 over. Okay, and we try with inverses to use arc sine, arc tan, arc cos rather than sine to the -1 to avoid that confusion. So they are 2 completely different functions, so don't confuse them. So let's start by thinking about the graphs. Now I think these graphs are easier than the inverse ones. Okay. If we are going to start with cosec, so if we remember, cosec is 1 over sine. Okay, so the easiest way to approach this is to have the sine graph sketched first. So I've got it here in radians. Okay, it doesn't really matter whether you look at radians or degrees here, because we're just getting this shape. Okay, so here's y equals sine theta, and cosec is 1 over that. So if we just look at some key points here, let's use a blue pen. If I've got 0 here, 1 over 0 can't do, so we know that's going to be an infinite point, and in fact we're going to have an asymptote there. So let's put an asymptote in there now, so we know that's going to be an asymptote. Okay, there's going to be no value at that point there. If we travel up to this point here, which is pi by 2 or 90, we get the value 1. So 1 over 1 is 1. So cosec of 90 or pi by 2 is 1. We get that value there. Then we come back down to 0. So if we look at the point here, which is pi, again it's 0, and 1 over 0 we can't have, so we'll have another asymptote here. The next point we've got is -1, so 1 over -1 is -1, so we'd have a point here, and then we'd have 360, and that's 0 or 2 pi, so we'd have another asymptote at 2 pi or 360. So we've got 3 asymptotes there, and we've got 2 definite points, so we now need to think about what's going on between the asymptotes and that point there. So let's get a pen. Okay, so what we've got here is some small values that are getting bigger. So when I do 1 divided by a small value, I get a very large answer. Okay, as these values increase, these values are going to decrease. So even if we think about sine 30 or sine pi by 6, that value would be 1/2, and 1 divided by 1/2 would be 2. So we'd have a value around here, and the same around here. So we can sort of see the shape is going to come down like this. Okay, and then it's going to come round here It's going to touch at 1 and come back up, and then we've got that asymptote there. Okay, so that's that part of the graph. And then similar idea over here. It's going to come up from minus infinity. It's going to touch there at -1 and come down. It's not very symmetrical, sorry. It should be more symmetrical than that. See if I can... Okay, so down like that. Okay, hopefully yours is a better picture than that, but anyway, so we've got this idea of 2 parts, okay, and of course then that would repeat. Okay, over here we'd come this U shape, and over here we'd have the N shape, and here we'd have the N shape, and here we'd have the U shape. Now, as with most graphs that have asymptotes, you must draw them in and make it clear where they are. Okay, so key points here. Firstly, where the asymptotes are. Secondly, our minimum and maximum. So we've got a minimum here of 1, sorry, and a maximum of -1. Okay. You also need to be aware of the period, that actually this complete cycle takes 2 pi or 360 degrees, so the period is 360. Okay. We need to think also about the range. Okay, so if you remember, the range is the set of output values. Well, these output values from here are 1 and above, so it's anything above 1 here and anything below -1 here. Okay, but there is never an output value between -1 and 1. Okay, so there's nothing in this section here and in this graph. Okay, so that's the graph of y equals cosec theta, and you need to be aware of that one. Learn it. Okay, but like I say, the easiest thing is you know the sine graph is to work it out from there. So let's have a look at sec. So again, sec is 1 over cos. So we start with the cos graph. Okay, so similar idea. We need to think about where these asymptotes go. So wherever there's a 0 on the cos graph, we can't do 1 divided by 0, so we're going to put an asymptote in. So we've got 1 at pi by 2 and 1 at 3 pi by 2. Okay, we know that at 0 the graph is cos 0 is 1, and 1 divided by 1 is 1, so we're going to have a point here. And similarly at pi we know the value here is -1, so 1 divided by -1 is -1, so we'd end up with this idea here. So we get this half of the u at this point. Okay. If we're just going from 0 to 360, we'd get this shape here again, if I can get it symmetrical this time. So it touches at -1 and then comes back down, not very symmetrical. Okay, and then we'd get this part here, touching at 1 and stopping there. Okay, at 2 pi. So it looks similar to the Coset graph, but of course it's been translated across, just like the cosine and the sine graph are similar, just translations of each other. Okay, so that's your sec graph, but again, things to think about. The period is 2 pi, and the same as the Coset graph. The minimum is 1 and the maximum is -1. Okay, let's have a look at the cotangent graph, or cot graph. So again, what I've got here is the tangent graph, and cot is 1 over tan. Now this has already got asymptotes in, okay. So I've done different coloured asymptotes for the ones we're going to need here. So we'll just look between 0 and 2 pi again. So firstly, at tan 0 is 0, so 1 over 0 is going to be infinity. So we've got an asymptote at 0. Then here at pi, we're going to have another asymptote because that's 0. And at 2 pi as well, we're going to have another asymptote there. Okay, so we know our graph is going to be heading off in that direction. Okay, so how else am I going? What else can I? Okay, so let's have a look at these values here. So this is pi by 2 or 90 degrees. Okay, now the moment there's an asymptote there, which means it went off to infinity, so 1 divided by infinity, the reciprocal of that is 0. Okay, because 1 over 0 is infinity. So I'm now going to have a value here. Okay, and I know I've got an asymptote here. So this graph does this sort of pattern. It's almost like there's like a reflection of the previous graph. That should go through 0. Okay, and then it's going to come down here, and then it's going to go that way. So it's like the tan graph that's been reflected and translated because the asymptotes are in different places. Okay, and then from here we start down here, and where there was an asymptote before, I go through there at 0. Okay, and then we come down here. So it's similar shape, but it's the reflection and it's been translated across. Okay. So things to note. Again, just like the tangent graph, the period of this is 180 or pi. It repeats every pi. There aren't any maximum or minimums. And it's just, the key thing here is getting the asymptotes in the right place. So let's have a look at the type of questions you can be asked. So first of all, let's think about domain and range. So if you remember when we were in lesson last week, we talked about domain is your input values and range are your output values. So for the Coset graph, okay, what this is saying is we can put any value of theta in, so R is for real numbers, okay, so we can put any real number into the Coset function, except we can't put 0 in, okay, because we'd end up doing 1 divided by 0. We can't put plus or minus 180 in, or plus or minus 360, or so on, or plus or minus 540. So all of those that go up in 180 degrees, we can't put in here. So our domain is everything except those values. And the range is the set of output values. So if you remember, we said actually the outputs, which are y, are greater than or equal to 1 or less than or equal to 1. Okay, but they're certainly not between minus 1 and 1. So this is your range. Sec theta is similar. So again, anything can go in except theta at plus or minus 90, plus or minus 270, plus or minus 450, and so on, adding 180s on. Okay, but the range is exactly the same. Y is above 1 or equal to 1, or less than or equal to minus 1. So the cotangent graph, again, same notation, any value can go in except theta equals 0, 180 or 360. Okay, so multiples of 180 again. And the output, so the range is anything. Y can take any value up to infinity and down to minus infinity. So there's no restrictions on the range. So the other thing we need to think about are reminding ourselves of our transformations that you would have done earlier this year and at GCSE. Because part of today's work is to draw the reciprocal functions, but also draw them after they've been transformed as well. So let's have a think. If I've got a function fx and I add a number to it, okay, that affects the graph by a translation 0b. So in other words, the whole graph shifts up the axes by b. Okay, so this is saying you've worked out your y values, now you're adding b to your y values, so they're shifting up. Okay, this one, x minus b, so when b is within the brackets as part of the function, it's still a translation, but it's to the right or left. Now this is minus b here, so this is a translation b0, so it's b to the right. Okay, so taking away b from x translates the graph to the right. If I have the function and I multiply the function by a, okay, we get a stretch parallel to the y-axis of scale factor a. So again, I've worked out my y values and then I multiply them by a number. So the y values change their position by a scale factor of A. Okay, if, and I've written this in two different ways, if I have a function and I'm dividing my input by A, okay, then the graph is affected by a stretch scale factor A parallel to the x-axis. So if it's inside the function, it's going to be parallel to the x-axis, but it's going to be the opposite of what you think. So x over A gives you a scale factor of A, or the other way around, if you're multiplying A by x, the stretch is 1 over A. Okay, so it's opposite to what you think. These two here making the graph negative, so if I work out my y values and make them all negative, that gives me a reflection in the x-axis. If I make my inputs negative, then the graph is reflected in the y-axis. And the last one we talked about last week, if I'm finding the inverse of a function, it's the graph fx reflected in the line y equals x. Okay, so for this example, we're asked to sketch the graph y equals sec x minus 1 over this interval. So let's think about how this has been transformed first, and then we will think about what the graph sec x looks like. So we're saying our function that we started with is sec x, but the y values we're plotting are fx minus 1. It's our function subtract 1. So if you remember from our transformations previously, when I add or subtract something, okay, then that affects the graph by moving it up or down. And in this case, it's going to be a translation of 0 minus 1. The whole graph is going to move down 1 unit. Okay, so now I know what the transformation is, I need to think about what does the graph y equals sec x look like. If we remember, sec x is 1 over cos. Okay, so let's think about the cos graph first. So the cos graph at 0 starts at 1 and goes through 0 at 90, and then it goes down at 180 to minus 1, which is 70, 80, down to minus 1. So I've got some key points in here. Don't need to draw all the points in, just getting an idea. And coming this way, it will cross here at minus 90, and at minus 180 will be minus 1 again. Okay, so if you remember, the sec graph is 1 over that, so I'm going to end up with some asymptotes, because 1 over 0 we can't do. So I'm going to have an asymptote here, because that's when the cos graph was 0, and I'm going to have an asymptote here, because that's when the cos graph was 0. I know my graph is going to touch at this point here, okay, and at this point here, and at this point here. So I'm going to very roughly, and you might want to do this bit in pencil, sketch in what y equals sec x looks like. So this asymptote suggests we come down here, okay, we go quite flat there and back up there, okay, and then here I'm going to come up, come up to that point there, and similarly we're going to come up to that point there. Hopefully your graphs will be a little less wobbly than mine. Okay, so that's what sec x looks like. What I've got to remember though is now I've got to translate that 0 minus 1. So it means the whole graph is going to come down 1. So instead of touching at 1, it's now going to touch at 0. And instead of touching at minus 1, it's going to touch here at minus 2. Okay, so you won't be able to shift down like I have. You will have to draw in another graph, which is why you need to make your first graph in pencil and your second graph much clearer, and label them really carefully, or do them on separate axes. Okay, so this is the graph y equals sec x minus 1. So let's think about the minimum point. So the minimum point is now 0, 0. Okay. Oops. Okay, and the maximum point is now -2. Okay, so the coordinate is -90 minus 2, or sorry, not -90, -180 minus 2, or 180 minus 2. It doesn't, either would be fine. So we'll put 180 minus 2. Okay, so they're the coordinates, or you might just want to put -2 and 0 as the maximum and the minimum. Okay, so the period of this again is still 360. It's repeating every 360. Okay. So I've just gone into Desmos quickly to show you what it should look like. So you can see that this graph actually flattens off quite a lot. It's not like a parabola, it flattens quite a lot down here and goes back up. Okay, but you can see the minimum here is 0 and the maximum here is -2. Okay, so this example asks us to sketch the graph y equals cosec half x over the interval 0 to 2 pi. So if cosec is my function, so function is cosec x, then the points I'm plotting are y equals f of half x. So if we look back at our transformation graphs, we can see that if I multiply x by a half, that will give me a stretch in the x direction, or parallel to the x-axis, but the scale factor will be the reciprocal of a half, it will be 2. So the transformation is a stretch parallel to the x-axis, scale factor 2. Okay, so we need to think about what the cosec graph looks like. We're going to need to put some asymptotes in. So if you remember, the cosec graph is 1 over sine. Okay, so I need to think about the sine graph. So I know the sine graph starts at 0, 0, at pi, which is 3.14, it's also 0, and at 2 pi, which is 6.3-ish, okay, here we get 0, 0. At pi by 2, okay, we go up to 1, so pi by 2 is just over 1.5 at here, so we're at 1 here, and at 3 pi by 2, okay, we're at -1. So 3 pi by 2 is about 4.7, so we're -1 here. So that's some key points. We can sort of see the shape there of what the sine graph looks like. So now we need to put in the cosec graph. So I'm going to put the asymptotes first. So the asymptotes are going to be wherever sine was 0. So I'm going to have an asymptote here, an asymptote here, and an asymptote here. Okay. The graph is going to touch at 1 and -1, so it's going to come up, go across here and go down, and vice versa that way. Okay. So let's change the colour. So we're going to come down here. We're going to touch at 1 here. Oops, a bit too low. Try that again. We're going to touch at 1 about here, and then we're going to skeet back up there in that direction. Okay, and on the bottom we're going to come up here, we're going to touch at -1 there, and oh, not very symmetrical again, skeet down here. Okay, so it is quite, this is probably better, it is quite flat at this point here. Okay, I'll show you a correct one in a minute, but that's what the y equals cosec graph looks like. Okay, that's not the one I need. What I need is y equals cosec a half x. Okay, so that is a stretch parallel to the x-axis, scale factor 2. So that means everything's being stretched from this y-axis here along this direction, okay, and everything is getting twice as wide, okay. So that means this asymptote here will be stretched. At the moment it's at pi, it's going to end up at 2 pi, okay. So this part of the graph we don't need, it's going to be outside our domain, so we can get rid of that. And this graph here is going to be stretched. So again, the minimum point was at pi by 2. The minimum point now is going to be at pi. So I'm going to draw a point here. So pi is about 3.14. So the new minimum point is at 1 and it's here. So if I just choose a different colour, I'm going to get rid of the blue one so we don't get confused, but that gave me an idea of shape. Okay, if you're doing this in an exam, what I would do is draw in pencil lightly your original graph and then do it really clearly, the graph you intend to be marked, and label as well is always a good idea. So this is going to start with the asymptote here, but it's going to take quite a long time to get down to this point here. And that's our minimum point, and then we scoot back up to this asymptote here. So for the domain, that we were given, which was 0 to 2 pi, this is all I have to draw, okay? Because we were stretched by scale factor 2. So there's only one minimum point, and it's 1, okay? And it occurs at pi, so it's pi 1. The period, okay, so the period is normally 0 to 2 pi, okay, or 0 to 360, but because this graph has undergone a stretch of scale factor 2, the period will be 0 to 4 pi, okay, so it will take 4 pi for one cycle of this graph. Okay, so for this example, we've got to sketch the graph y equals cot x minus 1 over the interval of 0 to 2 pi. So again, let's think about what the transformation is first. So if our function is cot x, then we're looking at f of x minus 1. Okay, so the transformation of the graph said that when we were changing the input, then that is always affects the graph in the x direction, and in this case it gives us a translation, okay, of 1, 0. So it moves 1 to the right along this x-axis. Okay, so we'll start by sketching the cot x graph, and then we'll think about translating it. Okay, so if we remember the cot x graph, we need to think first of all, where did the tan graph equal 0? Because the cot x graph is 1 over tan x. So the tan x graph crosses at 0 and 180, which is 3.14, and at 360, which is 2 pi, which is 6.3. Okay. So I know I'm going to have asymptotes there because we're doing 1 divided by 0. So I've got an asymptote there, an asymptote there, and an asymptote there. I also need to think about where the asymptotes were on the tan graph. So there's an asymptote on the tan graph at pi by 2, so that's just over 1.5. So that's now going to be where the cot graph goes through 0. Okay, and then there's an asymptote at 3 pi by 2, which is about 4.7, so that's now going to be a 0 point. So if you remember, the cot graph is a reflection of the tan graph, so it starts here, comes down like this, goes through at that point there and back down here, and then similarly we come down here, through here at 4.7 and down to this point here at 2 pi. Okay, so that's the cot graph. Okay, I now need to translate that 1, 0. Now with this, remember it's not just the graph that translates, the asymptotes translate as well. So this asymptote is going to move across to 1, and then this graph is going to move across there, which means where it crosses the x-axis is going to change. This asymptote here, which is at pi, or 3.142, is going to move across to 4.142, and then the graph will move, and so on. So this will move as well, but it's going to be outside our range. Okay. So because we've moved across, okay, our interval, our domain was 0 to 2 pi. So the graph has moved across, it's gone beyond where we need it to. So we don't need this bit of the graph here after 2 pi. I don't need to think about that bit there, so I can get rid of that. Okay, but I do need to think about what's going on this side of the graph. Okay, so the other asymptote, if we were moving backwards, so the other asymptote would be over here at minus pi, or 3.14. It would cross the x-axis here at minus pi by 2, which of course is minus 1.5, just over 1.5, 1.57. We're adding 1, so that takes us to here. So we're not going to quite reach the x-axis. We just need to draw a line that comes up here and looks as if it's going to head off to cross the x-axis here. In fact, we don't want to go beyond 0, so I'm going to cross that a little bit off there. Okay, so it just gets an idea. You do need to think about where it's going to cross the x-axis over here to make sure you get that in the right place. But that's what the graph looks like in the interval 0 to 2 pi. Because we've moved over, we need to think about everything moving over. Okay? So again, if I was doing this in an exam, I'd get the initial working done in pencil and then make it really clear what my final answer is. Okay, this is a difficult one, but the key to it is to shift everything over, start with the asymptotes, shift the main parts of the graph over, and then just think about either end, what happens. Okay. Okay, the final example is to sketch the graph y equals 2 cosec 3x over the interval 0 to 180. Okay, now I've got two things going on. I'm doing something within the function, changing the input, and I'm multiplying the output as well. Okay, so in terms of fx, this is what we're considering. Okay, so we need to think about what these two things do. So the 2 on the outside is going to be a stretch parallel to the y-axis. The 3 on the inside is going to be a stretch parallel to the x-axis. Okay, and we just need to think about scale factors. So the transformation is a stretch parallel to the y-axis, scale factor 2. And it will also be a stretch parallel to the x-axis, but this scale factor will be a third. Okay, because 3x means we're going to be dividing by 3. So again, let's just think about what cosec looks like, and then we can think about stretching it. Okay, so if we remember, cosec is 1 over sine. So I need to think about where the asymptotes are going to go. So the asymptotes go where the sine graph is 0, which is at 0. And 180 and 360. Okay, so although it's just 0 to 180, I'm just going to do the whole thing for now and then think about what's going on. So now I need to think about where the maximums and minimums are. So the sine graph has a maximum of 1 at 90 degrees. So 90 degrees is here, and the maximum of 1 is here, which makes that going to be a minimum of 1 for our cosec graph, and it has at 270 it has a minimum of -1, which will be a maximum of our coset graph. So I can get that sketched in now. Okay, as carefully as I can. Remember, this goes quite flat here, and then we can come back up here, and then similarly here. Okay, it's flat there, and then back down there. Again, very symmetrical, but you get the idea. Okay, so that's what our coset graph looks like. Now I want to stretch this, okay, so we'll start with the stretch in the y direction because that's easier. Now remember, everything's stretched from the x-axis, okay, so the only thing that doesn't move is the x-axis, everything else moves by a scale factor of 2. So these points are up here are just going to get steeper because they're just going to be stretching away to infinity. The key point is this one here. It was at 1, it's being stretched, so it's now going to be at 2. Okay, oops. So I'm going to have a new point here, 92, and my graph is going to come down to there. Okay, so the minimum now is going to be 2. Similarly here, the maximum was at -1, it's now going to be at -2. Now I need to think about this stretch scale factor a third, okay? So let's think about the minimum point. The minimum point at the moment is 90, okay? If we're having a scale factor of a third, I need to divide 90 by 3, which gives me 30, so this is going to be where the new minimum occurs, okay? I also need to think about the asymptote. The asymptote at the moment is at 180. I need to divide that by 3, which gives me 60, so the asymptote now is going to be here. Okay, so you can have a picture of what's going on. Okay, the asymptote here is at 360. Divide that by 2, it's going to give me 120. Okay, this was at 270. If I divide that by 3, I get 90, so my maximum now is going to be at 90, which is here. It's going to be 2 here. Okay, so I'll leave the red graph in for now, but this is what the graph is going to look like. Okay, so there and there. Oops. There we go, get the idea. All right, now issue is I needed to do it from 0 to 180. At the moment I've only got up to 120, so I need to do a little bit more. I can see that the period of this graph is 120 degrees. Okay, so I need to do, I'm not going to do a full other cycle because that would take me up to 240, which is too far. So I'm just going to think about the difference between these asymptotes at the moment is 60. So the next asymptote will be at 180, which is where I need to finish my graph. Okay, what's it going to look like? Well, I've started here and then I've done this bit. So the next bit I need to draw is like this. So again, I'm going to come down to 2, okay, at 150 and back up again here. Okay, it's 150 because we started at the minimum point here was 30 and we've just said the period's 120, so if I add 120 on, that gets me to 150. So the blue graph is what we need, okay, the red graph is just working, but again, if you're doing this in exam, do your working lightly in pencil and do your graph really clearly and label it for as the one you want to be marked. Okay, so the period we've said is 120 degrees. Okay, so hopefully that you've understood that. What I'd like you to do now is turn to page 266 and have a go at exercise 4.1. There's 7 questions there and different graphs to sketch.